let me just introduce my lightning talk. I won't take long because I'll be just rotating quickly. So, hello, and that's the lightning talk about meta rotate. This talk is based on Circle, which is a C++ compiler written from scratch by one guy. It's very impressive work. Wouldn't use it in production because it's not open source. It's a closed source, but a lot of things are working there, like whole C++ 20 concepts are there, reflection is there, and the new meta model for the reflection as well, code generation. And it's capable of compiling standard C++, Boost, and a lot of things. So it's really impressive work, really neat stuff. And it compiles much faster than Clang and GCC, and it's available on Gopel. So that's the introduction, what I'll be talking about. And I pointed out that it has a reflection, and it's doing that by having these add attributes. Like here, you can see on the line 2, add type string, where you have print types, and you want to pass, multiple types, and you just want to print them with the full expression. In C++ 20, it's basically impossible to do that nicely without type ID.name, which is unspecified and will give you mango name, or treat with the pretty function, which is not standard, because we don't have reflection. Circle has it, and it's super simple. So if you call it with the bool, int, and float, it will print as you expected, bool, int, and float. So that's pretty cool already. So that was just introduction to Circle. All right, now let's rotate things a bit. So in my opinion, the most compelling use case for Circle meta model, which is actually proposed to C++ as well. There's a proposal for adding this capability to C++, is this meta keyword, add meta. And you can see here that what is doing this line. So we have the first one, we have to mark it with this add attribute. We have the types, and we can get dynamic types, which creates meta objects from this immediately expanded tuple. So in C++ 20 or 23, that's impossible. Like you have a type list and you want to expand it in place into something else. In Circle, you can do that. So you have a tuple, bool, int, float. You say dynamic type, and you see ... at the end, which will produce dynamic type of bool, int, and float. And that'll be a meta object, which will be stored in the array. And the implementation behind it is basically a AST pointer to AST, like a pointer to AST3 in the Circle compiler. Having that, we can easily pack it and print it. So notice here that we actually moving from the kind of value meta space into type space by expanding it in place with pack type attribute. So pack type, we get the types, ... expanded in place, that produces boolean and float, and we do print types again, and we get boolean and float. So that's super cool, right? Because we have an array of types. Notice that array is not a tuple, it's an array of the same kind of type, which is a meta type. And right now, what we can do with it, and that's obviously rotate, because why not? Notice the only thing, the only difference here is the attribute, because that tells the compiler that it can operate on these meta objects. But besides that, we can use STL, which is like the huge win of template metaprogramming, right? Because the main problem with TMP and manipulating types is doing actually the TMP because it wasn't designed for that. And it's Turing complete. Although that's overrated, as Ben will probably point out. Interesting. So the rotate, it's a function from STL which might be applied for the types, the meta types which are stored in the array. So here we begin next and then that's just a rotate kind of thing which we have to pass. And types are taken from the array, which is the meta objects, which stores the pointer to AST. So when we do that, we can then again go back to types with pack types and get the int float bool, which is the rotated by 1 from the next in the second line on the previous code snippet, meaning that we will rotate left by 1. So bool in float becomes in float bool. So right now we now challenge to the users, implement that in C++ 20. Not super simple, I'd say, especially if you want to rotate, take a view or something like that. Like here, you have all the STL available to you, and you can do whatever you want. So that's super cool. We can even apply next algorithm afterwards. So rotate, and after that, accumulate, whatever. It's super powerful in my opinion. And if you had reflection and capability like that in C++, I think that would be super awesome. So yeah, let's the meta programming, and it's obviously rotate. And if you're interested, you can find Circle on the circlelang.org, and Gopel has the Circle compiler available, so you can click that one here, and you will get to the compiler, which will be Circle here. And it's super fast to compile and everything. And that's the example which I provided. Super cool stuff. And with that, I'll just thank you.
So yeah, I guess a little bit of background here. This is going to be a pretty like thinky talk and not a very like hands-on codey talk.
Wait a second. What are you expecting us to see right now?
You should have my slides.
I see Jonathan has started screen sharing, double-clicked into full screen mode.
How about now?
Hey, there you go. All right, start over.
It paused itself. But yeah, still on the first slide. You guys didn't miss anything. So this is kind of a thinky talk. Basically, the past 2 years for me, like for many other people, has been pretty difficult just in terms of like departures from routine and that sort of thing. And so I found myself spending a lot more time focusing on kind of my mental health. And in doing so, stumbled across Maslow's hierarchy of needs, which is a pretty common concept. But basically, there's this concept that you have this pyramid, and for each of these things that are to go up a tier, you have to meet all the needs in the tier below. So for example, you have air, water, food, shelter, right? Before you've got that taken care of, you can't really think about what you're going to do for work. Anyways, all this to say, it's kind of a progression. Around the same time, I kind of stumbled back across the testing pyramid, and got to thinking, like, I wonder if I can draw some sort of correlation between these two things. And in thinking about it, realized that our labels on these are actually in the testing pyramid are actually not correct. That unit tests hold no inherent value. That unit tests actually provide something to the effect of confidence for the individual developer. Whereas integration tests, I guess here it's labeled service test. I don't know. There's not great pictures for this. Anyways, integration tests allow interfaces between teams to have confidence, and system tests, end-to-end tests give the organization confidence that what they're delivering to customers is something that you're expecting. And so I would advocate to think about these a little differently, and instead of thinking, okay, we need unit tests, think, we need something that gives developers confidence. So if you're on a legacy project and you've got code that hasn't been touched for 10 years and has been working fine, it probably doesn't immediately need unit tests to have that developer confidence. That 10 years of like, you know, battle hardening is likely sufficient for that. And I would just encourage you to kind of think about what the ends is that you're trying to achieve, rather than dogmatically pursuing something because you saw it in a triangle.
So hi, I'm Charles. I work at LunarG. We make Vulkan stuff, ecosystem, the Vulkan loader. Can you see my mouse?
Yes.
Yeah.
Okay, the Vulkan, I'll be using it plenty then. The Vulkan loader is the thing I work on a lot. I did give a lightning talk like 2 years ago about Vulkan info, which is more Vulkan shenanigans. But if you aren't familiar, Vulkan is a graphics API. Think OpenGL DirectX. It's made by Kronos Group. So in the application ecosystem for Vulkan, there is your application, there are drivers that implement the API and do fancy things like drawing triangles. And then the loader is the thing that bridges the gap between them. And so I work on the red box in this image. And every Vulkan application goes through it. So it needs to be very well, it needs to be robust. It shouldn't crash and be bad and all that stuff. There's additionally a thing called layers in the Vulkan ecosystem, as you can see these brown boxes here. You can think of them like plugins to the API. So they can plug into the system and modify things. Well, the problem I had was the Vulkan loader, when I took it over, had basically no testing. It had some tests, but they were pretty bad. They were very flaky. The tests were written using the drivers on the system. So they had to work around driver quirks and other things. And so you couldn't really write a test and know that if this test passed, that means the code is correct. It's more of just kind of a general guideline. I'll add on top of that, the Vulkan loader code base is C99 and not very well designed for testing. It's like a single 8,000 line file for the most part. I'm thankful that the C++ test code, the tests were writable in C++. The big difficulty for testing the loader itself is how integrated it is into the host operating system. So many things the loader does touches the file system, the Windows registry, environment variables. It calls it to the OS system calls all over the place. And the tests that were written used non-modifying capabilities. So things like environment variables that could be set in the test itself. But it couldn't do anything that was destructive to the host. It couldn't go to the, like system 32 and muck around in there. It would not do that, and that'd be a very bad thing to do because, well, if your test fails or whatever, you've just ruined your entire installation. So the solution to all these difficulties, at least as far as testing goes, was to mock the world. Wait, not that kind of mocking. We need to figure out all the different inputs the loader has. So here's a quick rundown of them, but that also includes the drivers and layers that are on the system. We need to then intercept and or fake them, make sure that we can control those inputs. And if we can do that, we can reliably test the loader and give it situations so that it would test the actual code of the loader authoritatively and not just kind of, well, it worked in this case with this real driver that happened to make things happy. So the way the test architecture is now is there's a big black box, which is the framework environment. And this is where all the fancy magic that wraps the API is. The test code is taken the form of the application. The mock drivers and layers just kind of live around it and can be added and removed from it. So some of the things the framework environment does, I mean, it has to write to the file system. So it creates folders, write files into it. For Windows, there's the registry, which it has to read and write from. There's Windows driver APIs. There's several environment variables that I have to go find, clear out, and then recreate in my own fake world so that it won't bother the loader as it's being tested. And as I found out when I was deploying it to CI, the CI systems would run the loader in an elevated process state. It's like admin mode. And because the loader is on people's systems, if you're running a computer, I bet the loader is on your system right now because you have graphical output, and Vulkan's pretty common now. But admin mode is a security vulnerability, and it totally changes the behavior of the loader. So I also have to fake that, which is a fun side effect. Some of the fun Windows-specific stuff I did for the registry, instead of intercepting all of the functions that that interact with the registry and shimming and faking and DLL injecting them, there's a pretty nifty reg override predef key, which is like change root, but for the registry. And so I just create a key and I change my root to that, and everything from there looks like it was created. It looks like the root instead of it being a child, which is kind of cool. There are various Windows driver APIs, D3, DXGI, D3DM, KMT, one of those two. I use the Detours library, which is a free MIT open source Microsoft Research Lab DLL injection library. Very easy to use, highly recommend. Funnily enough, Detours uses a makefile to build it. It's a Windows library and it uses makefiles. I converted it to CMake for my own sanity. For Mac and Linux, the way the drivers are found on Linux and Mac is through the file system, whereas in Windows, it's through the registry. So on Mac and Linux, I have to do a whole bunch of redirection of the functions that interact with the file system. OpenDir, access, and fopen are the three, only the three ones I need to do. When I search for drivers and layers and whatnot, the DXG environment variables are used, and I have to replace them and figure that out. And it was pretty straightforward. One thing that wasn't was getting address sanitizer to work with everything, because I'm intercepting these file system functions and address sanitizer likes to intercept functions. Getting them to play nice with each other was a bit of a, I just did things, hit it randomly until it started working and then just didn't touch it. But when I ported it over to Mac OS, I found that it didn't work. Thankfully, when I started Googling around, I found some magical attributes that you give the linker and it will make it work. And I'm very thankful for that, because then I don't have to think further. Now I'm getting to the promised part of the thing about writing a fake driver in Vulkan. It's really not that interesting because it's the Vulkan API, but only the parts of it the loader needs for testing. Because the Vulkan API is big and complicated, I have to create a variable that holds all the state that the test may need, or that the loader may need. And because tests want to be settable by the test case, you have to load a function pointer, which will give you the address of this state object. And then once you have that, you can configure the test driver as you see fit. So that's how I configure the mocking driver to do what I need. I just load a function pointer, then I have access to the data itself. There is a wrinkle. While most things can be set at runtime, there are certain exported functions that differ. So there's different versions of the interface, and some versions have certain functions exported, some don't. So I have to create multiple binaries, each with the functions exported and others without. And I use a little bit of CMake and C++ magic to stamp out the variants and manage it all. But once I have all that, I can take it and apply it to the mock layer, which is the same thing as the mock driver in all realistic intents. So the test code is thankfully very straightforward. We create the framework that hosts all the shimming and interception. We set the state we want when we're doing a test. We call the Vulkan API functions we want to test, which call into the loader, which does a whole bunch of work, and then we check the results. And if they match what we think they should be, the test passes. An example test here would be checking if a layer is present. So we have env.add explicit layer, and we set all the configuration we want. So we're adding a layer to the system, and the loader should find it. And this enumerate instance layer properties function at the bottom enumerates the number of layers, and it sees that it has one and it should succeed. And that is a very quick rundown of trying to recreate the Vulkan ecosystem for a test framework. So thanks for listening.
So Turing Completeness, as you know, is often touted as some kind of yardstick of power in a programming language. And in online discourse, it's often implied or outright stated that if a language isn't Turing complete, it's somehow not a real programming language, right? I am here to debunk that idea. That idea is false. And to do that, I want to lay out what Turing completeness actually means and open your eyes to the high price that we pay for it. So cast your mind back 100 years or so. David Hilbert, he's on the left here, was into setting out challenges he thought the maths community should tackle. In 1928, he proposed solving the Entscheidungsproblem. That is, given a statement, can we devise an algorithm that tells us whether or not the statement is true in some axiomatic basis? And as you may know, that effort hit a snag. The grand plans of mathematicians hit a snag thanks to the other folks on this slide, Kurt Gödel, Alonzo Church, and Alan Turing. So, but before it hit that snag, or around that time, a lot of things happened. In the first half of the 1930s, in particular, Alonzo Church published the lambda calculus as part of the effort into this sort of grand theory of mathematics. And the lambda calculus was originally designed as a system of formal logic. Now, Church wasn't able to fully flesh things out on his own, and a few years later, his grad students helped out, as is often the way. J. Barclay Rosser and Stephen Claney showed that the untyped lambda calculus was inconsistent, meaning it was no good as a system of logic. It's inconsistent. That means there are statements you can make in it that lead to contradictions. You can derive both X and not X. So it's not suitable as a system of formal logic. And what is it that made it inconsistent? The key to proving this inconsistency is actually pretty famous today. Claney and Rosser discovered the Y combinator. And this introduces recursion into the lambda calculus. And the inconsistency arises from a situation something like Russell's paradox. When you allow self-reference, when you allow a predicate to act on itself, you get this kind of paradox. And if you know about Russell's paradox, the fix there is to introduce a notion of set hierarchy so that sets cannot contain other sets. In similar fashion, to fix this inconsistency in lambda calculus, based on what his grad students find, Alonzo Church introduces types. So here we are in the mid-30s. Claney and Rosser proved that untyped lambda calculus is inconsistent. And then, of course, in 1936 comes the next bombshell, which is that Church and Turing famously proved the equivalence of these three proposed computational paradigms. Gödel has recursive functions, Church has the untyped lambda calculus, and Alan Turing has Turing machines, as we probably know. By the way, it took Church and Turing a while to convince Kurt Gödel that it was actually equivalent, but they did, and they proved this. And so now we have this model of computation. They're all equivalent, and all of them, therefore, are inconsistent, as proved by Claney and Rosser. And basically, you can't have both arbitrary computing power and logical consistency. And where inconsistency manifests in Russell's paradox kind of as a contradiction, in computation, it manifests as infinite looping, unbounded recursion, that kind of thing. And so, of course, we know that the halting problem is insoluble, and this is why it's insoluble, right? Now, enter Haskell Curry, also in the mid-30s. He's on the left here. He first observes a correspondence between functions that take and return values and the notion of logical implication. And later on, William Alvin Howard fleshes out this idea and establishes the full correspondence between types and logical constructs like and, or, and implication. Now, this is the Curry-Howard correspondence, or the Curry-Howard isomorphism. And I said that by introducing types into the untyped lambda calculus, Alonzo Church fixed the logical consistency. You may have noticed the color photo of William Alvin Howard here. It actually took until about 1970 to fully flesh out this idea of the Curry-Howard isomorphism, the correspondence here. So the simply typed lambda calculus provides a consistent model of computation under this logical interpretation, right? And this is the difference between Turing complete and not. By using types in that way and giving up the ability to do self-referential arbitrary recursion, we fix the logical inconsistency that's inherent in the untyped lambda calculus and its progeny. So the question is, what do we lose by giving up that power? And the answer really is not a lot. We lose, just like fixing Russell's paradox, we lose self-referential ability, but we keep just about everything else. In particular, we keep things like structural recursion, we keep looping, we're working with types, but they're just not unbounded anymore. And there are lots of domains where this is all the power we need. Parsing, state machines, config, query languages. Most of the time, we don't need Turing completeness. The usual argument given for requiring Turing completeness is thinking about programs that are designed to run forever, like servers that respond to input and loop infinitely. But even there, I think there may be ways to model that in types. And the benefits we get from not being Turing complete are pretty large. Or, to look at it the other way, the cost of Turing completeness is high. So in sub-Turing languages, the halting problem becomes trivial. With a bit of care, we can perform some kinds of analysis and get bounds on computation and memory resource usage. There's also a social advantage. By restricting yourself to sub-Turing power, you're sending a strong signal that folks shouldn't try to abuse the language to do things that it can't. And I'm sure we can all think of many examples of language abuse, which is rife in any Turing complete language, because programmers are just that kind of people. Now, if you're thinking this is familiar, it's because this is precisely the influence that functional programming is having on modern C++ style. All the type-based approaches we adopt these days have their roots in these functional paradigms and the simply typed lambda calculus fueled by the Curry-Howard isomorphism. This is why we like modeling things with types properly. It allows us to reason about programs because we're avoiding Turing completeness. Sometimes in C++, you see people talking about algebraic data types, meaning std optional and std variant. They mean the new sum types. But in fact, all data types are algebraic. The algebra here is logic directly from the Curry-Howard correspondence. So sub-Turing languages, definitely still powerful, much more reasonable, quite desirable in many or most situations. On the flip side, accidental Turing completeness is something we see a lot, and it's probably the worst situation to be in. And there are many famous examples. They make for fun diversions because basically they invite abuse without really adding much to their domain. There's pages on the internet that list these accidentally Turing complete things. And, they're just useful curios because they're abused. So the next time you have a choice, the next time you're making a DSL or a general purpose language, consider this choice well. And it's important to know the trade-off you're making rather than accepting the idea of Turing completeness as axiomatic. This is the choice you're making. When you choose Turing completeness, what you're saying is, I've weighed out the options and I've decided it's important for my language to have foot guns because that's the only way that people will get things done. And it comes at a big price. So to finish, if you like the idea in this talk, please go watch a longer exposition. Paul Snively's talk on propositions as types. It's on the YouTube channel Papers We Love. This has been a very short summary of that talk in many ways. You may notice a couple of familiar folks in the front if you do go and watch that lightning talk, that full talk. Thank you very much.
Thank you, Ben.
Hi, today I'm talking about std_align, this little tool that I only heard about it recently because it only have this one niche use case, but when you actually need it, it's pretty nice to have this tool. So since it only probably have this one use case, custom allocation, I will talk about custom allocation. Consider this is probably the simplest custom allocator. It's not STL conformed, but whatever. This is arena. We have a pointer that represents a piece of memory that come from somewhere. And when we allocate, we basically just bump the pointer. Also, we keep track of how many sites will remain in this arena. This is a very simplified version of what std monotonic memory resource actually do. But it has pretty bad interface, but we can still use it. To use it, we provide arena with a buffer. It can come from stack, or you can pre-allocate a large chunk of memory. And then we allocate raw memory from the arena and then placement new actual object onto it. However, this code is completely wrong. Can someone yell it out? What is wrong in this code?
Does it take alignment into account?
Yeah, exactly. Yeah, because I'm talking about stud align. So yeah, it's in here when we allocate the 32-bit integer, it's 4-byte aligned. But since we allocate the 8-bit integer first, we just allocate the next chunk of memory at this 1-byte address, 1-byte out address, and then you definitely can't do that in C++. So every type has alignment. You can't construct object at aligned space. It's undefined behavior in C++. In practice, either processors will do some extra instruction to make it work, so it's really slow, or it's just blatantly not working. To fix that, we can have this little helper function that give a pointer and alignment. We can actually bump that pointer to an aligned pointer. You can see I do some pretty nasty things here. We cast a pointer into an integer, and then we bump this pointer by the alignment -1, and then use this bit mask. This is the same as modular operator, but since we are doing alignment is always power of 2, we can use this bit mask. And then we just cast the aligned address back as our final result. But the compiler will warn me if I cast the integer back into a pointer. That's why I use this trick, because of some pointer perseverance reason I don't really understand. So to use that align forward function, we just call we change our interface a little bit. We called it aligned alloc. By the way, if you call the standard function like just stud allocator alloc or like malloc, something like that, you don't need to worry about alignment because it will do the right things. But in here, we explicitly pass the alignment. And then when we want to allocate, we first bump our pointer. And then our final pointer will be our bumped by alignment pointer, but also add with the size. So this is our original pointer is at here, and we bump it into the alignment boundary. And then after we allocate, our internal state of the arena will be at here. But the previous code is pretty nasty. Especially we are doing some pretty scary casting pointer to integer stuff and some bit mask. So here enters the stud align. It takes alignment and size. That's exactly the parameters you need to pass into allocator. But also it takes a reference of the actual pointer and the space we required. So what it does is it will try to calculate if we have enough space to allocate size, but it will consider the alignment. If we can align, allocate that much size, then it will bump the pointer and reduce the size by how many bytes we need to align. However, it will not actually add a size to the pointer. So if we actually use it, we need to add the size ourselves at the end. And we still need to do a little bit of manual work. But if we use the align, then we have no reason to even think about alignment anymore. It will just automatically work. So that simplifies the code a little bit, and also we get rid of that scary helper function using the bitcast. And if you're not in 20, you even need to use reinterpret cast, and I consider it a win. So yeah, thank you.
Do you know if there's any function that tells you what the alignment is needed to be for a type?
Yeah, instead of align as, it's not, so align off. It's not a function, it's a keyword. Sorry,
Align.
not that, it's just align off.
Okay. I don't know that one. I have to look that up. Thanks.
Awesome. Thank you, Lesley. I think you would, yeah, and you would want that to be a templated function if you really wanted to do that automatically, like Marc was asking about.
Yeah, this part is what standard allocators actually hide from you. You don't need to do size of align of. Memory resource don't hide anything from you because it's just raw memory, but allocators will hide all those using templates.
Right.
So who's seen this, just by rough show of hands, who's seen this document, this image before? Just, I only see one, but I can not see very many people. Zoom is really. Okay, so we'll talk through this at some length then. So basically, when you're writing documentation, there's 4 types of documentation you can be writing. There's tutorials, there's how-to guides, there's explanation, and there's reference. Tutorials are kind of taking you through, here's like a potential use case, and running through like an imagined use case like that. Explanation is more like expressing design principles. How-to guides are like, here's a common task, let me lay this out for you. And then reference is like, I don't know, cppreference.com, like literally everything on there is reference material. So I was recently considering how it would be possible to kind of converge some of our testing with some of our documentation while allowing our documentation to also be verified. And I stumbled on this pretty cool library. It's written in Go, but it, you just compile it and produces a little command line utility that will take Markdown and based on annotations that you apply to your code blocks, create files for that. And I thought that would be really useful to solve this particular problem I was having. So I went and I played around with it a bit, and it turns out it's really neat, and I want to talk to you guys about it. So I imagined the simplest possible tutorial, or the simplest possible, like, I guess this would end up being a tutorial that you would be writing, where you're defining like talking about how to define and declare a function, right? So you've got some exposition, you talk about why you might want to do it. None of that's really terribly relevant. The interesting parts are, oh, can everyone see that? Do I want to big this up a little? Okay, cool.
Yeah, it's okay with me.
The interesting parts here are the code blocks, right? So we define so as most people I think know, you can say tick, tick, tick in Markdown to define a code block. And then if you put a language specifier after that, that'll annotate some syntax highlighting.
John, are you showing us a terminal or a Vim window? I hear you typing, but we're seeing a web page.
Yeah, hang on.
I think you're just sharing Chrome.
Okay.
Okay.
So
yeah, and making it a little.
Yeah, you definitely need to make that bigger. There you go. That's better.
I don't know what anyone can read. That was already big for me. There's the triple backtick syntax, and then you can annotate that with a language specifier. The Markdown, I believe it's Markdown like specification, also defines that you can put stuff after that, and that will and that's what the Markdown translator uses. So what it's going to do is you're going to give it a file name, and it'll create, and then it's just going to dump whatever you put in here into that file. So here, you know, continuing with the example of separating the definition and declaration of a function, because it was the first thing that popped into my head. I define a function, and then I talk a little bit about how to do declaration, and then I declare a function, and these contents will be dumped into a file. It also lets you do cool things like you can actually say CPP, and I can say, I think it's plus equals foo.hpp, and anything that I put in here will be appended to the end of that file. So if you want to gradually build up an example across a couple different code blocks, that sort of thing can be done. There's also facilities for, you can define things that'll be replaced in. So you could say, if you have like the same set of headers that you want to use everywhere, you could say tick 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 CPP headers, and then in your code block you just say, and it'll just drop in replace that. And there's a whole bunch of functionality like that. At risk of, you know, that this totally just devolving into the whole syntax of the language, I'm not going to go into that. The docs in the GitHub repo are super helpful. Instead, I'm going to run you through how to integrate this into CI. So I did this with Bazel just because I wanted to play with Bazel some more, and it's been a minute. All of this stuff is literally just to compile the command line tool. Don't worry about it. I don't really understand it. I stole it from some Medium article. The interesting parts are these two rules. So this rule depends on the output of the generated binary, and then it depends on this example.md that I just showed you, and it produces the two files that are listed in this example. And this is just a little bit of command line shenanigans to invoke the tool and then put the files in the location that Bazel is expecting. And then we use those files, create a CC library, and if I build foo, you guys will see that there was an error that I bet some of you noticed. In this file, we actually say that we want to include bar.hpp, which doesn't exist. We switch that to foo, run this again, and now we have compiling. You can naturally, you could take that compiled binary and do whatever you want with it. For our purposes here, for keeping it simple and keeping me in my time limit, I felt like just building it was sufficient. But yeah. Questions?
Wow, that's pretty awesome, actually. I haven't seen literate programming really demonstrated like that in a while.
Yeah, it's really neat. I have a couple of interesting ideas for this that I'd like to apply it for, but documentation feels like the lowest hanging fruit.
Yeah.
Are there ways to put boilerplate that don't show up in the documents?
Yes. So you can do hidden content. It's kind of gross. You have to do it in an HTML comment. But you could define like a hidden section, and then if you do that section, if you apply that section somewhere else, it won't show up in your rendered markdown, but it will show up in the file output.
This is awesome. I have so many markdown files that are like this, but I have to go and copy and paste, and then, you know, they get out of sync.
Mm-hmm.
Yeah, that was exactly. I've been frustrated so many times, like going through someone's docs, and I'm like, oh, this looks like it was not touched for 2 years, and no one knows that like all of these paths are totally wrong, and now I have to like work them backwards, and it's just that little bit of extra friction that makes the experience really frustrating.
Safe access to private data. Here we go. So this is a real quick follow-up to the talk I gave at CPPCon. And the talk was about all the things that can go wrong when you're writing unit tests and what to do when things go wrong when you're writing unit tests. And don't lose my mouse pointer. There we go. The structure of my talk was based on this slide from Schlock Mercenary, which is my favorite comic strip. It's a galactic grand space opera, aliens, spaceships, and all that. And here they're about to go do something they know is going to go wrong. So plan A is just a blade of armor that probably won't protect plan B, which is going to take a bullet for plan C, which is why we need more letters. And so what we did is we started with a common problem when you're trying to write unit tests, usually for legacy code or something. But so here someone's trying to build their own version of vector for some reason. It's got a capacity in it. It's got some logic about how that capacity grows when you push back and it's out of space or whatever you're doing. But we left out the capacity member function. So you need to unit test this, and you like to unit test this using the public interface, which is the thing you're always supposed to do, but you can't because this doesn't have one. And so we started to go through all the plans that that apply to this. So first of all, something like test-driven development or just designing for test would have prevented this, but that's already failed for some reason. And what we did is we then went through plan A, plan B, plan C, plans D1 and D2. We started doing white box testing and throwing out everything. And it's like, we're just going to reach in and test the damn thing. And those of you who heard the practice version of this back in August will recognize this slide. This is the point at which we're out of other good options. And this is the best we can do. And basically this scenario comes up under probably rare circumstances where you're not allowed to touch the original code. You can't change the original code at all. If you could change the original code, you wouldn't have to do this. But in this case, yeah, this is your best option. You need to unit test this, but you can't change the source code at all. This might be, maybe there's legal reasons or regulatory reasons why you can't change the source code, something like this. And we all know that this is not a good idea. And we know that that there are reasons it's not a good idea. It works to the degree you can apply that term to undefined behavior. I mean, it kind of works. We think it works. And by the way, back in August, some of you nutcases pointed out that you actually have to do this too. Define class struct in order to, you know, and at this point, things are just horrible. And at this point, all the good jokes were coming in the talk. It was right before Halloween. I was making jokes about horror movies and all this kind of thing. Right afterwards, several people actually, during the rest of the day, came up and told me that there is a way out of this. There's a way to get access to private data without invoking undefined behavior. Andrei Petrusenko, I think, was the first person to approach me. And he may be here tonight. I don't know, Andrei, if you're here. He was going to try and come. Some other people pointed this out. Andrei also sent me an email with his solution to it, which I didn't understand. And I spent a month trying to figure out. And found several other blogs. The links are there. Herb Sutter had talked about this a little bit way back in Guru of the Week 76, but more in the context of, here are some ways you can break things, don't do this. But then, of course, Dave Abrahams is, as in so many other ways, ahead of everybody else by about a decade. And so I'm going to show you his solution, which is up there on GitHub from about 10 years ago. And so I just want to walk everybody through this. Whether you can really get into your head why this works or not, I don't know. It took me a while, but at least you will have seen this and you'll have some clues. So over on the left is our vector class. We need to get to the capacity member data, which is private, so we can't get to it. So we're going to go from here. We're going to work our way up through the code you would write. Then we'll, once we've done that, we'll work our way back down and get to the real magic behind this. So our solution is to include a bunch of magic stuff, which is out of Dave Abrahams' code. We're going to make a tag type called capacity tag. And the only thing that it holds in it, it defines a type that is this. And you read these from right to left. So this is a pointer to a member of vector that is a size t. So this is a member pointer. Of course, this is the most horrible syntax in C++, right? You can read it from the other way if you want to. It's a size t member of vector pointer 2, right? Okay, fine. Then we do this thing here, and this is just absolute sheer magic. Okay, this is an explicit template instantiation of something called stow private. I'll show you what stow private is in a minute. But we're explicitly instantiating it, and it has two template types, or two template arguments, rather. The first is that capacity tag we just defined, and the second is actually the address of the thing we want access to. You shouldn't be able to type this, but you can. We'll come back to that. Having done that, the net effect is that there is something called stowed, which templated on a capacity type has a thing in it that is a value that holds this pointer, and you can use that as a pointer to member to get into V's capacity and do anything you want to it. You can read it, you can write to it. These can be functions, you can call functions, you can get virtual functions, you can do anything you want. All right. All the access control has gone away at this point. We can do whatever we want, no undefined behavior. All right. And you're asking yourself basically this: what the hell is this that we're looking at? So let's work our way back up through this, and I'll show you kind of where this came from very quickly. First of all, this is the stow private business. And stow private, if you're not familiar with templates, and probably even if you are, this looks like gobbledygook. So what do we have? So it's a template struct called stow private. It has two template arguments. First is a type tag, which is going to be our capacity tag down here. The second thing is a value called X. The type of X is a tag type. And that template there is just, that type name there is just because the template needs your help to know that that is a type name. So it's a struct. It has a constructor, which does something slightly mysterious, which we'll come back to. And then it declares a static member variable of its own type. You can do that. And when you declare a static member variable in a template, you need to define that someplace. You actually have to make the variable exist somewhere. In a normal non-template thing, you typically do that down in the .cpp file where you have to like actually instantiate that object. With templates, you have to follow it up with this gobbledygook. This stuff is just so that this static member variable exists and its constructor runs and does that. All right. What is this stowed tag thing that's doing sitting here? That is yet another type that we declare. It is super simple. It is templated on a tag, and it just declares a static member variable called value that is of type tag type. This line here is, again, just making sure that a template class that has a static member variable instantiates the member variable. That is a whole lot of template gobbledygook. What the hell is all this stuff? What we do is we declare a struct called stowed, and it stows a member called value. So this is a value of some type, of type tag type. Our tag is capacity tag. Its type is the pointer to the thing we want to get access to but can't. And as it turns out, that value is going to be the pointer to the protected thing that we can't get access to. So we declare stowed, stow private. The only reason this exists is so that its static member variable will be constructed, and its constructor stows the value that it is typed into stowed, templated on the same type, its value. So having done this, when I have a capacity tag whose type is the pointer to this, which we can't get to, and we instantiate stow private with the actual pointer to that, stowed ends up holding the pointer to the thing that we can't get access to. And the magic is all sitting right here. This is an explicit instantiation of this stow private template. And it turns out that explicit instantiation is the only place in C++ where the access specifiers get ignored. This is the only place where you can write this expression outside of the class itself and have the compiler let you get away with it. This, it generates the static instance of our stow private with a tag being capacity tag and loads into the appropriate stowed this value. Yeah, then it works, and you can use all of this stuff here as a pointer to member and get in there. What the hell is this? There is a C++ rule that says you can do this. This is what it says in the C++ 20 standard. Here it is. I don't know why this is here. Honest to God, I don't. I would love for someone to tell me why this is in the standard. I have no clue. I'm just about out of time, so I will quickly pass on to the fact that some people dislike C++ for its complexity. You don't have to look far to find them, right? All over the internet, maybe a lot of your colleagues. Some people who love complexity for itself and therefore love C++, no judgment. But there's a whole lot of us who dislike the complexity but are damn grateful when the complexity delivers close air support to cover your And so that is the way out of the horror slide from my talk. Thank you very much.
So I've been playing with web scraping in C++, and been writing a helper library that takes, Google has a library called Gumbo that will process HTML and give you a nice tree structure. And they're super nice about, it lends itself to iteration, which gets us to the first part here. You might notice that there's in a lot of screen caps, you'll see like first colon, last colon. That's C-line being awesome and putting the parameter name in. It's not some funky syntax. Okay. So what we need for web scraping, we got to retrieve the documents, parse the documents, query documents. I got a little curl wrapper like everybody else. It's got a few things. And that's all we need to talk about getting the documents for now. So with Gumbo, we get the document tree, and from there, I have a Gumbo iterator that will do a DFS walk of the tree, and from there, I just made a helper range type that gives you your begin, end, and there we go. The links, I'll post the links to this, but there's the links to the library that wraps it and all that coming up. And so from there, we need to do some querying and stuff. So what I developed was a bunch of predicates types where you can go over attribute, class type, ID, inner text, outer text, context, and the tag. And you can, and then through and did the operator overloaded for and, not, or, XOR, so that we can do things like match all, match any, negate match, or match one. And then you also have your brackets and that in there. So you can now do complex logic with these. And this part actually using findif and that, I kind of changed that about 2 hours ago and built some filtering iterators so that this gets a lot easier. And because the iterator, outside of generating the tree, which the library does, it's not going to it's not going to allocate unless you ask it to. There's a couple of places where it'll return a string. So let's go over some examples here. We want to find all the div tags. So you have the document range, begin and end, and we want to match the div tags. And this div is actually a function object. And that's it. Inner text for now needs the raw source because the tree that they give us refers back to it has pointers into the document. Or if you want to find all the links that contain a keyword, so here we're looking for all the anchor links that where the value starts with href, where href starts with HTTP and contains keywords. Keywords just a container of string-like things, and it just outputs into Markdown like. And I'll show you this running in a moment. And this is so similar. So you can see how we're combining. So, you know, it's a paragraph tag and its ID is ID. I guess in this case, we don't really need the paragraph because ID is unique in HTML. And there's some code. I just wanted to show some code. Here we go. So one more example that's the new one here. Where to go? And if this is too small, just let me know. Right, so we have I just created, it's just an item, and here's a plug out to JSON link. And this is, so I mapped it, so this items class into JSON, so we could generate JSON here. So I'm gonna go out to Newegg and find and search for iPhone 13 Pro. Generate the range document, and I'm gonna create a vector of items. I could have done this a bit with a transform. Didn't this time. So here we have that find iterator, and it's going to look for all the classes that are item container, which if you go into the document, that's where all the items that show up on the search page were within. And then from there, I'm going to go within its children and get a range and get another range iterator, and I'm going to filter over those. I'm going to look for where it's an anchor link. And so what this filter one iterator does is it'll take a list of predicates and tell you, return the value and tell you which one was found. So here I'm looking for the item title and the current price. And yeah, that space was there. That threw me for a few minutes. So then, so it finds the index. So the first predicate was found. It's just adding that, and then it's going to push back after it finds the price, because they were always in that order. It could have been, it could have done that a different way, but it was kind of weird. And then output them, and then we can just go like so. Let's get rid of all these breakpoints. Add one here. Let's just look at this one. And you can see so it just outputted a bunch of JSON data with all those URLs, the titles, and the prices. And that's about, oh, now let's go back to the, oops. It's hiding my window here. There we go. And so where I want to take this is I'm gonna, over the iteration, it's still using the C libraries node types. I want to do a C++ class on that where things are, you're not having to call the free functions, and then look into things like Puppeteer, Selenium like thing where it processes the JavaScript in the DOM, and you can go that way in the future. And that's that.
All right, so a nice little war story here, so that if you see this, you're not as surprised as I was. So Matt gave a talk a year and a half ago when it was still summer and nice in the beginning of COVID, and it's about correct by construction and how to make your APIs easy to use so that junior developers can't make a mistake, and some of us senior developers don't make as many mistakes. Looked at it, said, yeah, that's really cool. I'm going to play with some of his ideas. And I was going to do publish subscribe at work, so I figured, okay, I'll implement it and see how it works out. So 3 implementations: straight legacy implementation, the standard one. Subscriber says, send me messages to the publisher, and when you're finished, it'll say stop. Pretty straight, normal. Played with a slightly friendlier version where now I get a subscription object. So the subscriber says, okay, I want messages. Publisher says, here's a subscription object. And as long as it still exists, you get the updates. When you destroy the subscription, it automatically stops it. So this way you can use a Spark pointer and insert it into your subscriber. When the subscriber dies, the subscription dies automatically. The only problem with that was if the publisher died first, then you have dangling pointers. So using a weak pointer, same idea, except now that if the publisher dies first, it doesn't really matter when the subscription dies. All right, so how about performance, right? There's a lot of overhead here. It was really nice. Implementation was nice. Using it was nice, but is it going to cost how much? As we all know, there's no such thing as a free lunch. So what did Matt have to say about performance?
Onto the widget. So this is visible to the compiler. It's almost no performance, should be no performance impact. I haven't really talked about, but none of the things so far I've talked about have any reasonable performance impact in my experience.
All right. Well, it stopped. All right, hit the wrong key.
It's onto the widget. So this is,
come on, next slide. There. So the question there is, what is reasonable, right? Reasonable for one man is not reasonable for another. So I ran some experiments. I had the 3 treatments, 5 benchmarks. You know, how long does it take to create, destroy the instance, subscribe, unsubscribe, updates? Well, I'm going to be talking about create. 2 measurements, CPU time and wall time. And in my world, CPU time doesn't exist. All I care about is wall time. So I'll just work with that. All right, ran it through Google benchmark. And the thing that kind of surprised me was the simplest code, the legacy implementation was the slowest code. So that didn't really make any sense. So I played around, and just changing the order of the execution of the 3 benchmarks changed the results. Now the simplest code was the fastest code. So that didn't really make sense. I'm thinking, you know, maybe I've got to download in the background or something like that. So put on benchmark reputations 50. And again, changing the order made a difference on the rankings of the 3 tests. So at that point, I kind of left it for about a year and got into other things in my life. When the call for presentations came out, I said, okay, you know what? I'm going to randomize the order and modify Google benchmark to have it randomized. Start working on the code, and all of a sudden, someone else had the exact same problem, and they just finished it up this summer. So there's a new option to Google benchmark. It's not on the release product, but it's in the main called Enable Random Interleaving, and it does exactly what you'd think it does. It runs the different benchmarks repeatedly in different orders. With that, the rankings started to make sense. Again, most complicated code was the slowest. So I ran with benchmark repetitions of 50 and the random and non-random. And I ran that 50 different times. And what I saw was most times the rankings came out as you would expect, but a few times the more expensive process would be lucky. It would just come out faster. So what that really is telling me is we have to go back to statistics. In the beginning of coding, it used to be common to say, I sorted these 1,000 punch cards, and it took me 30 seconds. And I sorted these ones, and it took me a minute and a half. Okay, your code's better than mine. Then we started looking at, you know, order n squared and order n log n. That was really good. And now we're back to using stopwatches because nobody could understand what the CPU is doing. So we're back to checking random stuff. So the takeaway for me is you have to run benchmark repetitions a lot. You have to start using this and enable random interleavings. You're going to need to have lots of executions, not 1 or 2. And you're going to have to do a statistical analysis on it. In my case, I ended up doing an ANOVA analysis, and I did find out that my method is slower as expected.